In this next video, we're going to look at numerical integration. And to start, I want to remind you of some things we did in previous sections. So if you recall, we talked a little bit about Riemann sums, and the idea behind these was we were going to use rectangles to approximate the area under a curve for a specific function over an interval from a to b. And the idea was we picked either left or right or midpoints. We found the values of the function at those points and then used those to create the rectangles. And so our area became the approximation of the width of each rectangle, which was our delta x, times the height of all of them added up. And again, if you recall here, delta x we found by taking the length of the interval divided by the number of subintervals, or the number of rectangles that we wanted to use. Okay. So this was kind of a crude approximation to the area. If you recall, how good the approximation depended on not only the number of subintervals, but also basically whether we were looking at left, right, or midpoints. Some of them gave us overestimates, some gave underestimates, some were pretty good approximations, but not for small values of n. Okay, so what we're going to do now is we're going to look at two other numerical integration techniques. And the main difference between these two and the Riemann sums is, again, Riemann sums were nice for any function. And we could check it by using our integration techniques, which we later learned. For the ones that we're going to talk about today, the idea behind using these is these are functions typically that you really can't find the antiderivative of. Okay? Now obviously, because we are going to have you practice these techniques and we want you to show you that they're actually working, we're going to give you some functions that you can find the antiderivatives of so that you can check your work. And we'll talk about how good the approximations are by looking at error analysis on them. Okay? So the first of the two methods that we're going to discuss is the trapezoid rule. And the difference here is, so the setup is pretty much the same. I've got some function over an interval from a to b, and I'm going to subdivide it into smaller intervals. The difference now is, instead of using rectangles, we're going to use trapezoids. And the idea behind using the trapezoids is, if I look at the difference between the rectangle and the trapezoids, I can see less of the area under the curve is missed or added to it at each step. So even here it looks like I've got a slight over approximation for this piece of the curve, but the difference between the curve and the approximation is much less than what we see with the rectangles. Okay, so this is going to give us something slightly better than what we had before. And one of the things to notice is, as I look through these rectangles, we can find the heights just like we did before. So obviously the first and the last, the height is going to be at f of a and f of b. And then for the midpoints, again, remembering this distance here is delta x, then the height for this one is just a plus delta x. And if we did it again, this would be f of a plus 2 delta x, and so forth up to f of b minus delta x. Okay? And as we look at the areas, so if you remember the area formula for a trapezoid, it says it's 1/2 the sum of the bases times the height. Okay? So here, if I look at the area of this first trapezoid, it's going to be f of a plus the f of a plus delta x, and then multiplied by 1/2 of the height. So I'm going to get a delta x over 2 out front. Okay? But then when I go to add the next one, I can see I'm going to get that delta x over 2, so 1/2 of the height. But then when I go to look at the bases, notice I'm using that same base again, the f of a plus delta x. So here I'm going to actually get a 2 in front of that, plus the next term, f of a plus 2 delta x. Okay? And when I move to the next one, same thing. I'm going to get another 2 plus delta x, and so forth, all the way up to that last f of b. Okay? So when I look at my formula for the area approximation for the trapezoid rule, I can see I'm going to take my delta x, so the length of the interval divided by the number of subintervals, divide that by 2, again that's coming from the half in our trapezoid rule, and then I'm going to get 2 multiplied by each of those interior trapezoid lengths. For the outside ones, I'm only going to use them once. For the first and the last trapezoid, all of the other ones get doubled. So there would be my formula for the trapezoid rule, much like what we saw with the Riemann sums. Okay, and we'll do an example of that in a minute. Okay. The next rule is a little harder to picture, and usually when you see this in a regular calculus textbook, you will see a proof along with it, because the picture of it is a little hard to imagine. It's a little bit more abstract. But the idea for Simpson's rule, which is our second numerical approximation method, is that we're going to use parabolic segments to approximate the curve. And the idea behind this is, it doesn't matter how good the trapezoid approximation is, I'm still using a straight line to approximate a curved line. And so there's always going to be a big difference, big in the sense of error, a big difference between the straight line and the curved line. So using parabolas, we should be able to approximate curved lines better with curved lines. Okay? So there's a couple of differences here. Obviously the first being that we're using parabolic segments to approximate the curve. But the second is that when I do this, I'm actually taking 3 points on the curve instead of just 2, like we did with both the Riemann sums and the trapezoid rule. So again, if I'm looking here, for each trapezoid, I'm only using 2 endpoints on the curve. For Simpson's method, we're going to use 3 of them. So if I'm looking here, I've got the 2 solid lines and the dotted line, and I can think of the parabolic curve that goes between those 3 points. And same thing here, if I look at the 2 dotted and the solid, I can look at the parabolic curve going between those 3 points, and so forth. And like I said, it's kind of hard to picture that or draw it out, but that's exactly what we're doing. Okay? So here, when I look at this formula, same thing, each segment is going to have length delta x. And so when I look at my area approximation using Simpson's rule, we're going to get the delta x over 3, and the 3 comes from the fact that I'm using 3 segments instead of the 2. Again, the first and last segment are only going to be used in that first and last approximation curve. But the other ones, I'm now going to use a couple of times. So in particular, this dotted line I'm going to use in the first approximation, the second approximation, and in the third approximation. And it almost looks like I should have a coefficient of 3 there. But because I actually need to have an even number of subintervals for this to work, right? If I look at the 3 units, I need 2 subintervals to get those 3 endpoints. So n here has to be even. Okay? And if n is even, then what happens is, even though it looks like I'm using it 3 times, I actually come up with another one because of the way the parabola works. So I'm going to get 4 of the next endpoint plus 2 of the middle one, or the third endpoint. I'm going to run out of room here, so I'm going to bring this down. And I'm going to continue that pattern, so going from 4 to 2 to 4 to 2, up until the second to last one. I'm going to get 4 of b minus delta x, and then back to the endpoint f of b. Okay? So similar to my trapezoid rule, if I'm looking at the same function with the same interval and the same n value, then the only differences I'm going to see in the formula are the difference between the 2 and the 3, and the difference between the alternating 4s and 2s in the Simpson's rule, and all of the intermediate 2s in the trapezoid rule. Okay. Alright, so let's look at a couple of examples. So let's look at this first example with f of x equaling ln of x on the interval from 1 to 4 using n equals 6 subintervals. And we're going to look at both the trapezoid and the Simpson's approximations to the curve. Okay? So just kind of getting a sketch of what this is looking like. If we look at our natural log curve, we know it's going to do something like that from 1 to 4. Okay? And so we really are looking at the area, this region in here. Okay? So if we look at that, we know that region is going to be bigger than 1. We want to get an approximation for this. So using trapezoid, and it tells us first we've got to find our delta x. Okay, so for both methods, that's the first thing I'm going to want to do. Delta x again is b minus a over n, just like with our Riemann sums. So in this case, 4 minus 1 over 6, which is 3 over 6 or a half. Okay, so using the trapezoid rule, our integral from 1 to 4 of ln of x dx is going to be approximately our delta x over 2. Now we need to find those endpoints. Well, again, if I'm looking at 1 to 4 with 6 subintervals, you can think I'm looking at half a unit for each of them. So I'm going to start at 1, twice f of 3 halves, twice f of 2, twice f of 5 halves, twice f of 3, twice f of 7 halves, plus my f of 4. And again, when I look at this, I know I have all of my terms if I've got the right number of subintervals. So I think there's 1 subinterval, 2, 3, 4, 5, and 6. So if I look, I'm looking at 7 terms, but I still have 6 spaces between them. So I've got all of my terms in there. Okay? From here, it's just a matter of simplifying. So I'm going to plug in my function values at this point. I'm going to clean that up. So 1/4. Now I'm plugging my values into my f of x. So f of 1, natural log of 1 is just 0. 2 times the natural log of 3 halves. 2 times the natural log of 2. 2 times the natural log of 5 halves. 2 times the natural log of 3. 2 natural log of 7 halves. And then finally natural log of 4. Okay? Now that I've got all of my trapezoid heights in there, now it's just a matter of simplifying. Here we can use logarithm properties to add these up. Okay, so we're basically adding, or in this case, when we add logarithms, we're going to multiply the arguments. So 3 halves times 2 times 5 halves times 3 times 7 halves. And then if you want that last term, you can pull out as 2 ln of 2. So we'll multiply that last one by a 2. Adding those all up, we'll get the 1/4 times the 2 times the natural log of 315. Okay, so that's just multiplying all those arguments together. And again, we can simplify here. This is going to equal 1/2 times the natural log of 315. Okay. For something like this, you can get an approximation with your decimal. Definitely for problems in WebAssign, you're going to want to do that. So our decimal approximation for this is about 2.8763. I'll just round it to 4 decimal places. Then we can do the same thing with our Simpson's rule. So there's our approximation for the area under the curve. And again, if we look at that, that seems about right. We know it's definitely bigger than 1. We can even assume it's bigger than 2, right? Because if we're looking here, this would be natural log of 4, which is definitely bigger than 2. Okay? Definitely bigger than 1. So looking at it over that interval, we can see it should be more than 2. Okay? So for our trapezoid rule, we're going to do the same thing, except again now we're going to use the parabolic segments. So we're going to change the denominator of our coefficient with a 3, and again we'll alternate 2's and 4's in there. Again, remember for your Simpson's rule, you need to have an even number of subintervals. So if, for example, this was n equals 5, that's just telling me I cannot use Simpson's rule. Okay? Okay, Simpson's rule will start out the same way. Get your delta x. This case, since we're using the exact same function and the same interval, our delta x doesn't change. Okay? So the integral from 1 to 4 of our natural log of x dx is going to be approximately our delta x over 3. We're going to take our endpoints, but again, now when we look at these middle ones, we're going to alternate their signs. From there, we do the same thing. So we'll start by simplifying this fraction. We'll make that a 1/6. F of 1 is still going to be 0. Notice now we get a 4 natural log of 3/2 plus 2 ln of 2 plus 4 ln of 5/2 plus 2 ln of 3 plus 4 ln of 7/2 plus our ln of 4. So at this point, again, just like with our trapezoid rule, we can combine the like terms there. So we'll get a 1/6. If I look at all the ones with coefficient 4, putting those together, I'll get 3/2 times 5/2 times 7/2, which will give us a 4 natural log of 105 over 8. And if we look at the ones with all the 2's in front of them, so again, this last one, again, we can think of as 2 ln of 2. So we'll have 2 times 3 times 2, which looks like 12. And so simplifying, we're going to get 2/3 natural log of 105 over 8 plus 1/3 natural log of 12. Again, that's a really nice answer, but to know if that's even close to the approximation we got, again, you might want to plug in and get the decimal approximation. And so for this one, when we do that, we're going to get 2.5496 about. And so you can see they're both a little bit more than 2. How do we know which one's a better approximation? Well, there's a couple ways we can look at that. And so the next example I'm going to use, we can actually talk a little bit more about that. This example, again, if I look at my function, at this point we don't have a nice antiderivative for that. You can use something like integration by parts, or you know, a U sub, or other methods like tables to kind of find that antiderivative. But I want to do one that you can actually find the antiderivative of, and it's going to look a little bit more like the ones that you're going to see in your homework. So in this next example, we are going to look at one that's a little bit more like what you're going to see in your homework and in WebAssign. And the main difference here is not the fact that the integration becomes a little bit more difficult. These are all functions that you should be able to find the antiderivative of using methods we've discussed. The main difference here is this is a function that we don't expect you to know the graph right off the top of your head. Something like natural log of x, or even some of the parabolas that you're going to see, you should be able to get a graph of those and actually sketch out what the region looks like. For something like this, you could point and plot it, but this is not one we expect you to know right off the top of your head. Okay? So let's start with the approximations. Just like before, the first thing I'm going to do is I'm going to look at our delta x, because again, that's going to be the same for both approximations. In this case, our interval goes from 0 to 2, and we're looking at 4 subintervals, so it tells me my delta x is going to be at half. Okay? So starting with our trapezoid rule, we can see that the integral from 0 to 2 of x over x plus 1 dx is going to be approximately our delta x over 2, again, because we're using the trapezoids. And then we're going to put in our function in pieces for our subintervals. So again, starting at the first one, which is 0, plus, in this case, twice f at a half, plus twice f at 1, plus twice f at 3/2, plus our f of 2. Okay, and again you can check, I've got 5 terms, which means there's 4 subintervals. Okay. Again, plugging in, so we'll get 1/4. Plugging in 0, we get 0. 2 times Putting in a half, we'll get a half over 3/2. Putting in 1, we'll get 1 over 2. At 3/2, we get 3/2 over 5/2. And at 2, we're going to get 2/3. Okay. Again, clean it up. That's not pretty. So 0 plus, looks like a third times 2, plus 1 plus 3/5 times 2, plus our 2/3. Okay. At this point, we're going to want to get a common denominator. Once we have the common denominator, we can add those together. You'll see our common denominator is 15. Adding that up, we'll get 53. And then our approximation looks like 53 over 60. So there's our approximation for the trapezoid rule. Okay. Now let's look at the approximation for Simpson's rule. Okay, so Simpson's, again, we will start out the same way. We know our delta x is a half, because that's the first thing we found. So the integral from 0 to 2 of x over x plus 1 dx is going to be approximately a half over 3, again using Simpson's. F of 0 plus 4 times f of a half plus 2 times f of 1, 4 times f of 3/2 plus f of 2. Okay. Again, notice it's the same values we had here. The only difference is we alternate some of those with 4s as their coefficient. Okay. So simplifying, we'll get a 1/6. Okay. Looking at our terms there, when we plug in, we're going to get exactly the same thing again. So the 3/2 over 5/2, 1/2 over 3/2, etc. Again, the only thing changing is the coefficient. So we're going to get a 0 plus a 4/3 plus 2. Oops, sorry, that should be 1. Because we're still going to get a half there. Putting in the 3/2, we'll get our 3/5 times 4. And then our last term again is still 2/3. Okay. Same thing, we're going to add all of this up. Now it looks like again our common denominator is going to be 15, but if you notice when you add these two, we're going to get 6/3, which is 2. So plus 1 is 3. So we're looking at 3 plus 12/5, which looks like 27 over 5. Okay. Multiplying through, this is going to give us a 27 over 30, which when we simplify gives us 9/10. Okay. So at this point we have these approximations. The next question should be how good are these approximations? Okay. Now again, this is one that we can get the exact area by using our integration techniques. Okay. So if I'm looking at the integral from 0 to 2 of x over x plus 1 dx, we can let u equal x plus 1, so du equals dx. Rewriting in terms of u, when x is 0, u is 1. When x is 2, u is 3. The x plus 1 on the bottom means that I get a u minus 1 on the top. Oops, that should be du. Okay. From there I can see that's 1 minus 1 over u, which antiderivative is going to be u minus the natural log of u. And then plugging in, we can see we're going to get a 3 minus the natural log of 3 minus a 1 plus natural log of 1, which gives us a 2 minus a natural log of 3. So this is our exact value of the integral. Okay. So let's look at some error approximations, or error analysis is another way you can think of this. So when we start talking about error analysis, there's 3 types of error that we can look at. The first is what we call the actual error. So if I'm looking at the area that we're trying to find the number for, and I look at the approximation I get, what is the actual absolute value difference between those two values? That's our actual error. Relative error gives us a percentage of how close our approximation is to our actual value. Okay, sounds basically the same. The difference here is it is a percentage of the error in relation to the actual value. Okay, whereas the other one is looking at a value and a value, this one is looking at an error and a value. Okay, and then the third type of error analysis we can do is looking at our bounds on the error. And that one's going to take a little bit more to talk about, so I'll wait till after we do the example here. So looking at what we just discovered, we found our trapezoid approximation to be about 53/60. Our Simpson's rule approximation was 9/10, and the actual area was 2 minus natural log of 3. And again, you can get a decimal for that. But let's look at these different terms I just mentioned. So we'll start with the actual error. Okay. So if I'm looking at the error in the trapezoid rule, what this is saying is I want to take the area actual value minus the area trapezoid approximation I got and take that absolute value. And that's going to give me my error in the trapezoid method. Okay? So here in this case, this is going to be 2 minus the natural log of 3 minus that 53/60 in its absolute value. So plugging this into a calculator, for these you are not expected to do these by hand. Okay, on an exam you're going to be asked other types of questions like how would you get the actual error, how would you get the relative error, things like that. So for this one, plugging in, I guess I should put an approximate sign here, 0.181. I'm going to round it to 4 decimal places. For your homework and your web assign, read it carefully because it's not always going to be 4 decimal places. Okay, but this is telling us it's about the difference between the two values we have is about 1.81%. Okay, if we look at the Simpson's rule, same thing. We're going to take the actual value minus the value we got using the Simpson's rule and take their absolute value difference. Okay, so in this case, again, we'll get a 2 minus the natural log of 3. We're going to subtract off that 9/10. Okay, again, plugging it into your calculator, we see that we get 0.0014. Okay, so this is telling us about 0.1% difference between the two values that we got. Okay, so looking at this, this is telling us for the same function, same interval, and same number of subintervals, our Simpson's rule is almost 10th better than our, or 100th better than our trapezoid rule. Okay. Now again, relative error tells us the difference between the error in the method and the actual value. Okay. So looking at this as a percentage, again what this is saying is if I want the relative error in the trapezoid rule, what I'm going to do is I'm going to take the error in the trapezoid rule and divide it by the actual value of the function. Okay, so in this case I'm taking that 0.0181 and here a word of caution. If you can leave the decimal, the original decimal, meaning this actual value in your calculator and then divide it out, you're going to get much better accuracy than approximations. Now, even though I'm writing 0.0181, when I do this calculation, I'm actually leaving the exact value in the calculator to get this. Okay, and then we'll divide out by the 2 minus the natural log of 3. So plugging this in, we see this gives us about 0.0201. So that's about 2% error. Okay. So our relative error in the Simpson's rule, same thing. We'll look at the error in the Simpson's rule over our actual value, which says again 0.0014 divided by our 2 minus the natural log of 3. When we plug that in, we're getting an approximation of 0.015. Okay, so again, much better approximation using Simpson's rule in this case than we would get with the trapezoid rule. Okay. Now in general, when we're looking at the two rules, if I have something that is much more curved in the general graph of the function, my Simpson's rule is going to be a much better approximation. If it has a more linear aspect to the graph, then my trapezoid rule is going to be much better. The last thing to talk about is the bounds on the error. And the bounds on the error can be used for two different things. The first is to actually get a bound for the error of your approximation. So if I know my function, I know the n value, and I know the interval, I can actually determine how good of an approximation it's going to be, or how accurate it's going to be within a certain decimal place. Okay? The other side of that is maybe I don't know the n value I want, but I know how good I want the approximation to be. So maybe I want my trapezoid approximation to be within 1/1000th of the actual value. Then I can actually use the bound formula to figure out what the n has to be so that will work. Okay? So the bounds on the error, there's two formulas, one for each of them. And it tells us first for the error in the trapezoid method. Again, given the fact that I know my function, my interval, and my n value. It says that if I look at the cube of the length of the interval divided by 12n squared and multiply this by the max on the interval of the second derivative of our function. I'm going to put absolute values on there because we really do mean the distance there. This will tell me how big my error can be. Okay? Or another way to look at it, how small I can get it. Okay? Now this formula seems very arbitrary. Again, if I was looking in a regular calculus book, they would actually go through the explanation of this. But the idea is I want my error to be small. If I'm getting error on the magnitude of 10 or 5 or 1, that's not a great approximation. If you recall, when we talk about error, we want error to be minimal. So we're thinking very minute, on the order of thousandths or hundredths or millionths if we can. And so looking at this formula, it tells us a couple of things. So if I take the length of the interval and divide by something like n squared, again, the more subintervals I have, the bigger n is. So the bigger n is, so for example, compare 1 and 10. If n is 1, I'm looking at dividing out that length of the interval by 12. Not too bad. But if it's 10, which isn't too different, I'm looking at dividing out by almost 1200, and that's huge. Okay. The other thing to look at is my f double prime, the max of that. So if you remember, to get the max of a function, we take the derivative and then we optimize that. So we find the critical points and then we find out where it's increasing or decreasing and get our maximum. In this case, if I'm maximizing the second derivative, that means I'm going to look at the third derivative and do those critical values. But more importantly, looking at the second derivative compared to the first means I'm taking a smaller value, right? If we think of our derivatives, if I start with x cubed and go down to x squared and then down to x, I'm decreasing the order of the function. And so this is making my function much smaller. Okay? If I look at Simpson's rule, we can see that the bound on the error is even more small. Oops, I don't need that. Okay, so here looking at this one, if I look, I'm now dividing out by n to the fourth. So again, if I'm looking at 10, I'm now looking at dividing out by a little over 1 million. And looking at the fourth derivative, well, for polynomial functions, if you think about the fourth derivative, if I'm looking at a cubic, that fourth derivative is 0. If I'm looking at rational functions, that denominator grows as I take more derivatives. So again, I'm looking at something very small here. And so looking at the max on that interval, will help us diminish our n value there. Okay, so again, the bigger the n, the smaller those are, but because I'm now dividing out or multiplying out things that are huge and dividing out by something really big, that means my Simpson's method takes less n subintervals to get almost the same approximation. Okay? So let's look at some examples of these. So in our first example for the bounds, let's look at f of x equal x cubed for n equal 4 on the interval from 0 to 2. We want to just find the bounds on both error approximations. Okay? Now I chose this one because it's very easy to get our derivatives. Obviously not all of the functions you're going to have are going to have such nice derivatives. But at least in here you'll see how to go about doing this. Okay? So the first thing I'm going to want to do is find my derivatives, because again, for my Simpson's rule I need a fourth derivative, but again, to maximize that I actually need a fifth derivative. So I'm first going to just lay out my derivatives. So again, if f of x is x cubed, that tells me f prime is going to be 3x squared, and f double prime is going to be 6x. Okay? For my third derivative, we're going to get 6, and then for our fourth derivative, we get 0. Okay? Like I said, I'm going to need to take this one step further because I need to maximize it. But again, if I take the derivative of 0, it's just 0, and it's going to keep going from there. Okay? Now I need to find the max on the interval. Okay? So looking at my second derivative, to find the max of this function, I need to look at the third derivative. Okay? And I need the critical values of f triple prime. Okay? Well, in this case, 6 is greater than 0, so it's positive. There are no critical values, which means if I look on the interval from 0 to 2, this is increasing. Okay? So the max is going to occur at the rightmost point. So let me write it this way. My max of f double prime on the interval from 0 to 2 is going to equal this function evaluated at 2. Okay. I guess if you're taking notes right now, I would say it this way, which is equal to that. Okay. We can do the same thing with the fourth derivative. So again, looking at the fourth derivative to get the max, I need the critical values here. Well, again, I'm looking at a constant function, which is 0 on 0 to 2. Okay? So basically it's the same everywhere, which means our max on 0 to 2 of f to the fourth is just 0. Okay? And another way to say that is, well, my function is 0 everywhere. The height of it is going to be 0 everywhere, so the max is 0 everywhere. Okay? So we've got our maxes. Now let's go to our actual formula. So we'll start with the trapezoid. So it says this is going to be less than or equal to b minus a. So again, 2 minus 0. We'll cube that over 12. N in this case is 4. And we're going to multiply by the max of the function on that interval. Okay? So simplifying looks like 8 over 12 times 16. Top is going to be multiplied by 12. Notice I didn't multiply that out because I'm going to cancel some things. The 12s cancel. So I'm looking at 8 over 16, or a half, which I'm going to write as 0.5. So this tells me if n is equal to 4 on the interval from 0 to 2, then my function x cubed is going to have a trapezoid error of at least, or I should say at most, 0.5. Okay? That's not great. That's telling me it's about 50%. For an error, that's a huge error. Okay? So this tells me a couple things. I probably want a bigger n value, or I need to pick a different interval. Okay? Alright, doing the same thing with our Simpson's rule, we see, again, b minus a over to the 5th power over 180 n to the 4th. And then we multiply by our max. Okay, now this one again, notice, I don't really care what that value is. 180 times the 256 divided by into 32. I don't care what that is because I'm multiplying by 0, which tells me if I look at this function, so x cubed, on the interval from 0 to 2, 4 subintervals is enough to give me an exact value for this curve. That's great. Okay? And again, we can see that it's going to be much better because I'm looking at something that's polynomial, which means it's going to have more curves in it than it has straight lines. And so on the interval from 0 to 2, the parabolic segments work much better than the trapezoids. Okay? So there's our error, finding the bounds on our error using the function, the interval, and the n. Okay? Now, like I said, we could go the other way. So as we saw, the Simpson's rule with 4 subintervals gives us a really good approximation. But again, because I'm looking at a trapezoid with straight line segments, it's not going to be a great approximation for 4 subintervals for that curve. So the question then would be, what n value do I need to get a really good approximation? And notice here, really good, I'm thinking 1/10,000th. That's not quite 0, which was what we got for Simpson's rule, but that's still really good. It means, you know, I'm really, really close, 4 decimal places out to the actual value. So let's look at this. So we can again use our bound formula to find the n value. So if we recall, e sub t is going to be less than or equal to our b minus a cubed over 12n squared times the max, I don't know why I keep wanting to write a line there, of our second derivative. Okay. Now I use the same function because we already found the max of the second derivative on the interval. So in this case, if I'm looking from 0 to 2, then I know our max on that was 12. That's what we found before. Okay? So to find our n value, what we're saying is we want 2 minus 0 cubed over 12n squared times 12 to be less than or equal to 0.0001. Okay? And at this point, you should notice this is just an inequality. We know how to solve these. Okay? First thing I notice is I can cancel off the 12s. So I'm looking at 8 over n squared less than or equal to 0.0001. Okay? Can multiply both sides by n squared and divide out by the 0.0001. Okay? Come up over here. So simplifying the left-hand side, it tells me that 80,000 is going to be less than or equal to n squared. So now I just have to take the square root of both sides. Notice in all of these operations, I haven't done anything that's going to change my inequality. So for all of them, my inequality is still going to stay the same. Okay, all of these are transitive. Okay, so square rooting both sides, square root of 80,000 is going to be less than or equal to n, which if we plug this in, we get about 282.8. Okay, now when I get my answer here, we've got to remember a couple of things about n. So first off, n has to be a whole number, right? N's got to be some integer value bigger than 0. So I can't have a decimal in there, okay? So n being greater than this for trapezoid rule tells me that n is going to have to be at least 283, okay? If I was doing this for Simpson's rule, so if I had a different function, I was trying to find the n, and I got this value, the other thing to keep in mind is that your n for Simpson's rule has to be even. So in that case, I would have to make this 284. Okay? So keep that in mind when you're solving for your n values. But what this is telling me is if I want to get a good enough approximation to x cubed on the interval from 0 to 2, I need 283 subintervals to do that. So n equals 4 is just not going to work. It's going to give me an approximation, but it's not going to be very good. Okay? So in your homework and in WebAssign, you're going to see much of these types of problems, and you're going to be asked to do things very similar. On the exam, you are going to be asked some of this. You are not going to need to memorize these formulas, meaning your bound formulas. Those will be given to you, but you should know how to use them. So you should be able to find the n value or use the n value like we did in the previous example to come up with what the error bound is.